Hello everyone. In this lecture and in next few lectures, we will be discussing the mathematical prerequisites required for the foundations of quantum mechanics course. So in this series or the set of lectures, we will cover the linear vector spaces, linear operators, and the representation, matrix representations, and stuff like that. So throughout this course, we will come back to mathematical methods, mathematical prerequisites, in which we will cover the tensor operators and whatever is required mathematically to understand this course. So today we will start with linear vector spaces. A linear vector space V is a set of vectors we represent by Vi, which satisfy certain properties. Those properties are the following. There is a linear vector space set of vectors over a field of scalars. The set of scalars, let us call them AI. These are vectors, these are scalars. So a set of vector Vi over a field AI is called a linear vector space if it is closed under vector addition and scalar multiplication. What we mean by that is, if we have a vector V and we multiply it with a scalar A, then also it's a vector from the same vector space, same set. The set V should contain, if it contains V, then it should all contain A times V for every A and for every V. Okay, not just that, if we have two vectors V1 and V2, then their sum, which sum is some abstract operation we have defined over this vector space. So their sum should also be from the same vector space, same set. So we can write one statement which contains both the conditions. A times V1 plus B times V2 should belong to the same set. So this is what we mean by closed under vector addition and scalar multiplication. Further, associativity. If we have three vectors, V1, V2, and V3, then it doesn't matter, it shouldn't matter in what order we add them, we should get the same outcome. Then there is a requirement of null vector. There should exist a vector 0, we call it 0, such that if we add it with any vector v, the resultant is the vector v. Okay, so 0 should also exist in this set. And if there's a null, there will be some inverse. The inverse vector for a given vector v, the inverse we define by v bar, such that v plus v bar is the null vector. So if we have a set of vectors, vectors can be any abstract quantity or any abstract mathematical structure, such that it can be worked out with the scalars, and we can define operations such as scalar multiplication and vector addition over that. Then that set of vectors can be called a linear vector space if it satisfies these four conditions. Okay. So there are a little bit more conditions, but these are the main four conditions which need to be satisfied. And if that satisfies, then we can call it a linear vector space. It has certain property which will be revealed as we go along this lecture, and we will know eventually. This can be very powerful mathematical structure to understand many concepts in mathematics in foundations of quantum mechanics. So to understand it better, let's take examples. So set of all the real numbers be represented by this R, and this is scale. This set is it forms a linear vector space. We have to define this. It forms a linear vector space over the field of real numbers. Okay, so if we have an x which is a real number from this set, then we multiplied with the scalar, which is also a real number, that also belongs to a times x also belong to R. So if we have x1 plus x2 or ax1 plus bx2, this is also a real number, so it belongs to R. So it satisfies the first condition, that is closed under vector addition and scalar multiplication. Now if we take three real numbers, it does not matter how we add them. If we take the definition of addition as the regular definition of addition, then it does not matter in what order we add them, we get the same number, so it satisfies the associativity. There is a null vector, that is the zero number, the real number 0, so such that if we add 0 with any number, we get the same number back. So that's the null vector, and for every real number x, there exists minus x, so the such that x plus minus x gives us the 0, so we get a inverse also. So set of real numbers also form a vector space over real field. Similarly, we can have set of complex numbers, we represented by C, over real field, it forms a vector space, over complex field, it forms a vector space. It's trivial to understand all this thing, we can do it ourselves. Slightly more non-trivial set example will be set of ordered set of two real numbers x and y. So this is represented by R2. So this we know it is the two-dimensional plane we can have. So any vector in this two-dimensional, any point in this two-dimensional vectors, two-dimensional plane is represented by x comma y. So that's the geometrical representation of R2. Now the scalars will be the real numbers, and if we multiply a vector xy with a scalar, we get another vector in the same two-dimensional plane. If we have, we can define the addition operation as x1 plus x2, y1 plus y2. So that would amount to having one vector, second vector. So and the sum will be given by this vector. So that is the vector addition we have defined in R2. So under this vector addition, we can see that it's closed over scalar multiplication and vector addition, because addition of two such vectors will give us another vector in the same R2. Then there is associativity. The three vectors we add in any form, any way, it does not matter, we will get the same answer. And the null vector will be the 0, 0, that is the origin of this two-dimensional plane, and inverse will be x, y, inverse will be minus x minus y. So in that way, it satisfies R2 satisfy all the properties required to be linear vector space. It's not enough to give the examples in favor to understand something. It's also important to give some examples which do not satisfy the criteria. For example, we can have R2 over complex field C, then it does not form a vector space, because if we have x, y, which is from R2, then if we multiply it with alpha, some complex number, then it does not belong to R2 because it's no longer real. So in that way, this is one simple example where we see that a set of vectors does not satisfy the linear vector space criteria. So R2 over complex is not a linear vector space. Another example which can be very interesting, which will be very useful for us, is set of n by m matrices, set of all the n by m matrices, complex matrices over complex field is also a vector space. If we take a matrix M, which is from this set, then M1 plus M2 will also be the same n by m matrix, complex matrix. So if we multiply it with alpha 1 and beta, alpha 1 and alpha 2, then also it's from the same vector space, same set. So if we check one by one all the conditions, we will see that for example, the null matrix will be the matrix of zeros, is the null matrix, and minus of m will be the inverse matrix or inverse vector. So in that way, we'll see that this set also form this set of n by m complex matrices also form a linear vector space. One of the very interesting subset of this is of particular interest to us, that is the Hermitian operators, Hermitian matrices. Hermitian matrices H, let us say, is defined as a matrix which is equal to its own Hermitian conjugate. Hermitian conjugate is defined as transpose and conjugate. So if a matrix is equal to its own Hermitian conjugate, then it's the Hermitian matrix. And this is interesting from quantum mechanics point of view, because all the observables are represented by Hermitian operators, Hermitian matrices. So this matrix, this set of matrices, Hermitian matrices, form a linear vector space over real field. Although the elements of the Hermitian operator or Hermitian matrix can be complex numbers, but it forms a linear vector space only over the real field, not on the complex field. So if we have matrix H1, which is Hermitian, and we have H2, which is also Hermitian, then we multiply it with scalar A and B. If we take the Hermitian conjugate of that, it will be A H1 plus dagger plus B H1 dagger, which is H2 dagger, which is A H1 plus B H2. So it's the same. It's the same matrix. So it's Hermitian. So in that way, it's closed over scalar multiplication and vector addition. Associativity, this is the simple addition of the matrices, so it does not matter in what order we add them. So associativity is trivially satisfied. The null vector, the matrix of all the zero elements is the Hermitian matrix. So that will be the null vector, and negative of a Hermitian matrix is also a Hermitian matrix. So that will serve as the inverse vector. So in that way, set of all the Hermitian matrices over real field forms a linear vector space, and this will be used extensively in the entire course. So with these examples, I hope we have a little bit of better understanding of what it takes to be a linear vector space. But we do not stop here at the definition of a linear vector space. We can introduce further structure over the vector space. That is, for example, we can introduce inner product. Till now, we had any operation involving two vectors was just the addition, which was the vector addition. But now we can introduce another structure, that is the inner product between the two vectors. So if you have an inner product is a mapping on the vector space. The inner product, let me represent it by I, which takes vectors of V and it map it to scalar. Scalar field is generally represented by F, so V goes to F. Okay, so it's actually V times V. So two vectors go to F. So we can define, if we have two vectors, V1 and V2 from the vector space V, then we write the inner product as V1, V2. Okay, it's an ordered set of these two vectors, and it satisfies certain property. First of all, the property is that V1, V2, which is a scalar, V1, V2 is equal to v2 v1 in a product, but not equal, it's a conjugate. So conjugate, in any sense we define conjugate on the field, so this will be one element of the field and it will be the conjugate element of the field. Typically the kind of vectors we are interested in, the field is complex, so then it will be a complex conjugate. So the inner product of two vectors will give you some complex number, and the inner product of the same two vector but in the reverse order will give us the complex conjugate of the same number. Now if we have a scalar times the first vector v1 and v2 the second vector, then it will be alpha star v1 and v2, and if we have v1 alpha v2, then it will be alpha v1 and v2. It means the inner product is linear in the second argument and anti-linear in the first argument. Okay, and then there are some simple relations v1 v2 v3 with three vectors, such that we are taking the inner product of v3 with the sum of v1 and v2, then it can be decomposed as v1 inner product v3 plus v1 inner product v2 inner product v3. It seems very trivial, but sometimes these properties can be very, very important. So throughout the quantum mechanics course or foundations of quantum mechanics course, we will be representing v1 v2 as v1, this opposite symbol, and v2. So this will be the definition. This is how we will be representing the inner product. Once the inner product is defined over a vector space, then certain structures or certain definitions can be given. For example, we can define the norm of a vector, that is given by v, the inner product of it with itself and the square root of that. That is, this is how we define the norm, which is basically the length of the vector in some metric. And we can show, like from the first definition of the inner product, we know that v is a real number. Not just that, v is also a positive number. Okay, and equality holds only for the null vector, not generally. Every vector will have non-zero norm other than the null vector. We can define the orthogonal vectors. That is, you have two vectors v1 and v2. They are orthogonal if the inner product is 0. Then they are called orthogonal. Normalized vectors. That if the norm of a vector is 1, then it's called a normalized vector. So if we have linearly independent vectors, if we have a set of vectors vi, then they are called linearly independent if sum over I, some scalars ai times vi equal to 0. This equation has the only solution such that ai is 0 for all I. Then only we call this set of vectors as linearly independent. What does that mean? Let us say there exists a solution where not all ai's are 0, and we get this. We can satisfy this equation by taking a set of ai's such that not all of them are 0. So in that case, we can represent, let us say, v1 as minus sum over I is not equal to 1 and rest is there, ai vi. So it means one vector out of these all vectors can be written as a sum of all the other vectors. So in that way, there is a, so let us say a1 was non-zero, so it will be actually minus 1 over a1, and then sum over I, ai, vi. So it means we can write the vector v1 as a linear sum of all the other vectors in this set, sum of these other vectors in the set. In that way, one vector depends on the other vectors. So in that sense, it's not independent set. So the independent set will be the one in which none of the vectors can be written as a sum of the other vectors. Okay. So what is the significance of this? If we get the largest set of linearly independent vectors in a vector space, okay, then the cardinality of this set, cardinality of this is called the dimension of the vector space. Okay. The cardinality, or the number of the maximum number of linearly independent vectors in a vector space, tells us the dimension of the vector space. What is the dimension of the vector space? For R1, the dimension was 1, because you have just one number which is one vector which is independent, and all other vector depends on it if you just multiply it with scalars. In R2, we need at least 2 vectors to represent all the other vectors. Okay, so in R3 it will be 3. In different vector spaces we have different number of vectors. Okay, so for example, and this I will insist that you verify, if we have 2 by 2 Hermitian operators, we said that Hermitian matrices form a vector space. So we consider 2 by 2 Hermitian operators, then we can write it as some A, B, C, D, and we can see if we put the hermiticity condition, then it will give us A and D in real numbers and B equals C star. So we can write an arbitrary Hermitian operator as A, B, B star and C. Now, what is the dimension of this vector space? We need to ask. And I'm giving you the example, or I'm giving you the answer, but please verify this thing. We can choose vectors. This is one vector. We can choose another vector. This is a Hermitian operator. We can choose another vector, which is a Hermitian operator. We can choose another 0, 1, 1, 0, and we can choose 0, minus I, 0. These 4 matrices are the Hermitian operators, are some Hermitian operators, and you can write any of the operators of this form as a linear sum of these 4 operators with real coefficients. For example, we can write H to be A times, let me call it E1, E2, E3, E4, the vectors. Okay, then I can write H as A times E1 plus C times E2 plus B plus B star over 2 times E3 and B minus B star over 2 times E4. So in that way, we can write an arbitrary matrix as a linear sum of these numbers. This should be I times. So we can write an arbitrary matrix H Hermitian operator as a linear sum of these 4 operators. So it means if I have a set of 5 Hermitian operators, such that 4 of them are E1, E2, E3, E4, and the 5th one is something else, then I can write that matrix, 5th matrix, as a sum of the 4 E1, E2, E3, E4. So the largest set of linearly independent vectors in the linear vector space of Hermitian operators will have the cardinality of 4, because you can have only 4 independent vectors in it. So it means the dimension of 2 by 2 Hermitian operators is 4. Okay, so dimension of such vector space is 4. So in later on we will be using this definition, the definition of these dimensions to characterize many vector spaces, and to talk about a few things which will be clear soon. So once we define the inner product structure or the linear vector space, there are many interesting properties which emerges out of this structure. One of the most useful is the triangular inequality. So it goes like this: if we have two vectors v1 and v2, then their norm v1 and v2, that is their lengths, in some sense the sum of their length is always greater than or equal to the sum of the length v3, sum where v3 vector is the sum of v1 plus v2. So the sum of the individual length of two vectors is more than the length of the sum of the vectors. So we can graphically see it like this: we have a vector v1 and a vector v2, then their sum, as we know from our earlier experience, the sum is represented by v3. So in this, the three vectors v1, v2, this is v2, and v3, they form a triangle. So basically what we are saying in this inequality is the sum of two sides of a triangle is always greater than the third side. It can be only equal when it's not really a triangle, when we have two vectors v1 and v2 collinear, and third one is also in the same direction. So that's the trivial case, but if we have a valid triangle, then the sum of the two sides is always greater than the third side. So this inequality is true in general for any vector space where we have defined the inner product in the using the definitions we discussed earlier. So to prove it, we start with something called Cauchy-Schwarz inequality. This is another very interesting inequality in linear vector spaces with inner products. So this goes like this: if we let us define a vector u which is orthogonal to v1. So how do we get this thing? This is orthogonal to v1 and it is in the same plane as v1 and v2. Okay, so how we define it? Then we can say u is v1 v2 minus v1 inner product with v2 over v1 mod square, the length of v1 square. Okay, now if we see the inner product of v1 with u, that will be v1 v2 minus v1 v2 over v1 mod square, which is actually v1 v1. This cancels and we have v1 v1 and we have v1 v1, and that's 0. So it means v1 and u are orthogonal. Now we can write v2 as u plus v1 v2 over v1 v1. So from here we can see that v1 v2 is a sum of two orthogonal vector u and v1, and rest is just a scalar. This thing is just a scalar. So v2 can be written as two orthogonal vector, and if we want to write it graphically, if we want to represent it graphically, we have v1, we have v2, and we have u, and we are writing v2 in terms of u and v1 with appropriate weights. So if we represent it in a slightly different way, it will be v1 with some scalar times v1 alpha, where this is alpha and this is u, and this will be our v2. So we have v2 v1 v2 and u forming a right angle triangle. So now we can use in a way the Pythagoras theorem, or we can just take from here we can see that the norm of v2 will be the norm of u, norm square of u, which is here, and the norm of this vector, which is norm of v1 times v1 v2 mod square over v1 mod square 4. Now this is a positive quantity, so we can say v2 mod square is always greater than or equal to v1 mod square over v1 mod 4 v1 v2 mod square. This implies that v1 v2 mod square v1 mod square is greater than or equal to v1 v2 inner product mod square, or v2 mod v1 mod is greater than or equal to inner product of v1 v2. What we have achieved here is that the inner product of two vectors is always less than the product of their lengths. This is what we are saying. So if you have two vectors v1 and v2, and you take the product of their length, that will always be greater than the inner product of the two vectors. Okay. So now what we will be using this relation in the following way. Take v3, which, let me remind you, which is v1 plus v2, then v3 mod square is v1 plus v2 mod square, which is v1 plus v2 v1 plus v2, and that is equal to v1 mod square plus v2 mod square plus v1 v2 plus v2 v1. So we have these four terms when we find the norm of the sum of v1 v2. Now v1 v2 is a complex number. If our field is complex, so we can write it as v1 v2, the norm of it, times the phase vector. So it's a polar decomposition of a complex number. Any complex number can be written as a real positive number times a phase vector. So exponential of I alpha is our phase, and rest is our so v3 mod square can be written as v1 mod square plus v2 mod square plus v1 v2. Just let me remind you that v1 v2 mod is same as v2 v1 mod, and we have exponential of I alpha, and that other one has to be complex conjugate, so it's exponential of minus I alpha, so, which is v1 mod square plus v2 mod square plus 2 times mod v1 v2 cos of alpha. So exponential of I alpha plus exponential of minus I alpha is cos of alpha, 2 times cos of alpha. So 2 times cos of alpha. Now just remember our earlier inequality that this factor is always less than or equal to mod of v1 and mod of v2, the product of v1 v2. But the whole factor we still don't know whether it will be less or more, because cos alpha can take value between -1 and 1. So it means we can say that v3 mod square is always greater than v1 mod square plus v2 mod square minus 2 v1 v2, no, minus 2 v1 v2, and it is always less than or equal to v1 mod square plus v2 mod square plus 2 factor here v1 v2. What we have done here is, if cos alpha is maximum value of this is +1, if we take the maximum value of it, that is +1, then replacing v1 v2 with v1 mod times v2 mod, then this quantity is always greater than v3 mod square. And if cos alpha is negative and the maximum negative is -1, then we replace v1 v2 with v1 times v2, then we get the lower bound on v3. So we get v3 between this quantity, which is v1 mod square plus v2 mod square minus 2 v1 mod v2 mod, and v1 mod square plus v2 mod square plus 2 v1 v2. We are for the time being only interested in this part, so we get v3 mod square less than or equal to v1 mod plus v2 mod whole square. Hence we get v3 mod less than or equal to v1 plus v2 mod, and this is what was our intention to achieve.